It is Krishnan Srinivasarangan. Hi,
Hi guys.
Hi, how are you?
Good. So it's the three of us, I guess. So
one more person was supposed to join, but I don't know whether he's joining or not.
Okay.
I will just check whether he's there.
Anyway, so just wondering. I got your email. I was just very busy, by the way, Nikhil. I got your email about the boost converter.
Yeah.
So I didn't have a look at it.
Yeah, actually, I cleared that doubt. Whatever I have made you, that issue is solved. But going forward, I am not able to complete the task. So let's see what is there. So should I start directly, or we have to continue with whatever we were doing in last class? We want to conclude that part.
Yeah, I think we should just finish that off, right? It'll be good to just finish it off once and for all.
Yeah, I mean that I can show, but maybe we can. I've got the answer. Okay. It worked.
Okay, great.
Project Euler. I didn't take much time. Okay?
That is the best part.
I was thinking that like the other guy was showing, it's not at all ending. I was like, okay, how long it is going? But after we did this customization, I think it's okay. I will see if I can share it.
So that is usually the trick behind many of these questions, that they try to have you think that, oh, this is something which is like going on and on, but really speaking, it needs like, they want you to write optimized code.
I think he he's okay. That's fine.
Okay, cool. So, yep. So you're computing the numbers.
I'm so sorry.
No, that's okay.
Yeah.
Previous sum, previous number, previous sum, range, previous number.
I can probably just quickly explain what I tried to do. Maybe there is some mistakes. So, so in the compute triangle number, we discussed that we should probably include some historical information. That is what was computed earlier, so that you can use that for future computation. So, I mean, what I did was, so until it could be any number until which we computed the last time. I mean, in the previous instance, and then you also give the sum. For instance, I was first thinking I'll just give the sum. But then I thought that it might be difficult to use it because I need the number until which we computed the sum, because the range will be from that number till the IDX plus.
Yeah.
And sum it, and then so for instance, essentially the idea is that you have 1, 2. You get, let's say you get sum until 1, 3, 6. Let's say you have this, and then the idea would be the previous number will and you want to compute the next one, which will be 10. So the next one will be 10. So we want to compute 10. So instead of so we will give the previous number here will be 6, and the previous previous sum will be previous number will be 3, and previous sum will be 6.
So in this case, this is perfectly okay, because we are always going incrementally. That is, we are always going to increasing numbers. If, however, you want to generalize this function for any application, when possibly you could even want to go down. So let's say you know the 9th triangle number, but you want to now compute the sixth triangle number. So you want to go down instead of up. In that case, this probably will not work because the range object will give you an empty list. So you will get back the same sum.
Yeah.
If you wanted to be more flexible in that case, then you would have to have some conditional clause. So what I would say is the best way to do this is you could just say that one, you will have to check if the previous number is greater than or less than this. In that case, you can return this. If the previous number is greater than the current number, then you have to now create a reverse range. So it will be range of previous number to this number and step -1, or you have to switch them either way.
Yeah, but in that case, you'll have to subtract, right?
Exactly, and also you have to subtract the sum. For this problem, this is about as optimal as it gets. But if you want to use this function in general and you want to consider that possibility also, then you can have that condition as well.
Yeah, but my question is, how do you store this previous number and previous sum?
Yeah, so I will show you because you haven't seen how I use it, because that's of course required because I put something. So what the idea is this. So in the find triangle number factors, which is trying to find given the number of factors, minimum number of given the number of factors, it tries to find the triangle number. So it is the topmost function. And in that function, the initial number is 1, and the previous triangle number, I am initiating it to be 0, which is the same as what I do in the function as well here, where previous number is 0. And then while I compute the triangle number, the initial number I am giving will be initial number -1. That is the initial number. How I am trying to do, I will show you that exactly. So I'm doing something. So I'm computing the triangle number. Let us assume that this is not there for the first iteration. When I start, this is not there. Let's say this is not there. You don't have to worry that this part is not there at the first iteration. So you find the triangle factors, and if the triangle factors is greater than the minimum factors, you quit. So when I increment the number, there's this initial number that I gave inside, and then I compute the previous sum. That is, I keep the history. That is, the triangle number is kept as the previous triangle number. Now this will go here as the previous sum, and the previous number I'm just going to decrement the current number that I'm giving -1. Which means, like, I have computed the triangle number until the previous, so I have computed triangle number until number 3, and now I'm going to compute it number 4. So for number 3, this is for number 3, this is number 3, this is the sum for number 3, and this is 4. So what I will do essentially is that this will be continuing, so that it will make use of the extra history information that the compute triangle number function takes. Is it okay?
Yeah. So basically,
the break command we have given before the initialization. So will it execute that initialize process, or it will go out of the while loop?
If this one is only if everything is done. So for instance, you have found the factors, the number of factors is greater than or equal to this 5. This, for instance, in our case, we need 500. The moment it reaches this 500 numbers, you don't need to do any of these anymore. So okay. You break out of the while loop and then you go.
Okay.
Yeah. So in this case, and that's how I will end up using this. So I will just see if I can do what was said. Yes. So we say previous number is less than or equal to idx, and then otherwise we give here -1. So this will be this should be more like idx.
Yeah, either way you can do either switch them or whichever.
Yeah. And previous number. Again, I think should it be -1, because the range object only goes until the last. I mean, it skips the last number, right?
Yeah. Basically, one of them should not be included. So it's exactly. So if you're starting the previous number, you already know. So or rather, the previous number. Yeah, sorry. No, the previous number you already know. So you want to calculate the new number until one number before that, the previous number. So the previous number you don't include. So if you use, like for example, in this case, the previous number is greater than the index, right?
Yeah.
So if you choose previous number, it will stop 1 before that. If you choose previous number -1, it will stop 2 before that.
Yes. Yeah. Oh, sorry. Okay. Okay. So, or rather, let's just keep it in the same way. Like previous number, since it is bigger, we start with previous number, and then we want to stop at idx minus. I mean,
it's like this.
Stops.
Yeah. So always the way to think about this is this: it will never stop at the ending number, right?
Yeah.
So
you one before.
One before. Now, if you're counting downwards, it will stop one greater.
Yes. So this is fine, but now I have to.
Again, I think it will not even be idx if you see, because you do not want to take idx into account. If you take idx -1, see, it's like this. It will take the number. It will check if the number is greater than the stop. If it is, it will add the number. Then it will decrement. It will again check if the new decremented number is greater than the stop. If yes, it will add. It will break the loop when the new decremented number is equal to your stop number. It will not add that.
Okay.
So if you put idx -1, it will add idx.
Yes.
So if you put idx, then it will stop at idx +1.
Yeah.
You can, when in doubt, pick out a Jupyter notebook and just play around with some numbers. That's the best way.
Yeah. So this again, this is also right. Right. So you have to subtract it from the previous one.
Yeah.
Okay.
That's it. Very good. So the only other thing is, in terms of compute factors, did you take that odd number thing into account, or it wasn't necessary?
Yeah. So what I did was, in the compute factors, so I did, I think we had already done that, the consider square factors only up to the square root. And include that. I think we had already done this last time. So what I did in this time was that, by default the step size was 1, but if it is not divisible by 2, then I put the step size to be 2.
Very nice. Yeah, then it's very convenient.
And then nothing else changes.
Yeah. So basically he's just said that if it is even, then he is going to check divisibility by even and odd. So you need increment of 1. If it is odd, you're only checking at odd numbers. So you're starting at 1. So which means you just need a step size of 2. That's it. Yeah.
So I think, so it actually was very fast. This is the number, and it was quite fast. I would even run it again.
It'll be interesting. I don't know where that person is. Maybe I'll post it on LinkedIn today. I don't know who he is. So if he is on my LinkedIn connection, he can comment and see if he got the number or not. But anyway. So I just since we are waiting for the
what way can we track the amount of time it's taking?
There is a time it function. There is a time it function. You have to just Google it. I think you have to Google it. It's a percentage time it. I very rarely use it.
Yeah. I mean, I see.
Yeah.
So, but you see, it's already done. So
yeah.
It's fine.
You can actually put this in for Project Euler and check if it's the right number also.
Yeah, it's done.
Good.
I checked it.
Okay, great.
Yeah, so I have got my first correct answer in Project Euler.
Okay, great. So that's great news. Okay, great. So just to conclude, anyone has anything to talk about? I believe a few other people have joined, so they can also join in. One of them is Darius, by the way. He's so.
Yeah, hi guys. Just coming in to see if I can soak up any knowledge just through osmosis.
Okay.
I need any smarts added that I can get, so I'm trying my best here.
All right. Okay. I guess there's one other person who's on mute and no camera, but I don't know if he has a webcam or a microphone. So if you want to say hello or something, you are welcome to. Yeah. Otherwise, I think if it's done, then I'll be happy to take up the next problem. We want to talk about something, anything.
Let's move to the next task then.
Yeah, sure.
Yeah. So shall I share my screen?
Yeah, sure.
Go on. I stopped sharing, so you should be able to.
Yeah. So basically, this is what I have done. Something I wrote on paper.
Okay.
So this is a boost converter, typical boost converter without any lossy elements and all. A very raw boost converter. So these are the parameters. Okay.
Mm-hmm.
So LCR values are not written here, but it is included in the code. Input parameters will be input voltage, output current, and duty ratio. Output parameters will be Vout and input current. Mm-hmm. And duty ratio and IO is calculated by this basic formula. So I have computed, written all the state equations and all, but I have for this presentation I have just written this steady state model.
So I'll just before we talk about this, I'll just go up and I'll tell a little about the circuit to Srinivasan, because the equations will be very, very clear to him, because this is like he's a control. But this circuit is a boost converter. Okay, so boost converter basically means it will take a DC input. Let's say, for example, you have a 5-volt battery. Example, you can take that 5-volt battery and boost it up to 12 volts. Right? So usually there are two types of converters very popular: buck converter, boost converter. Buck converter steps down a voltage, boost converter steps up a voltage. Right? Mm-hmm. So the basic way that this works is the first voltage that you see, VD, is the input voltage. So you connect that input voltage to an inductor, which is like a coil wound on an iron core, right? And then there is a MOSFET or an IGBT, some kind of semiconductor device which can switch on and switch off. So it can be on a low resistance path, which is like almost a short circuit, or a high resistance path, which is pretty much open circuit. So this is different from analog circuits where there is an active region. In power electronics, you always work in the cutoff region, that is high impedance, or the saturation region, which is like zero or negligible impedance. And then after that, there is a diode. Diode is similar to a switch, except that there is no control. In a switch, you can actually physically turn it on and turn it off, like a MOSFET. You can give it a gate pulse. A diode, which just turns on, turns off on its own. Only thing, it will conduct current in only one direction, and it will turn on when it is forward biased. So which means when the voltage at the cathode or anode is greater than the voltage across the cathode. Right? So, and then there is a capacitor, and the last resistor is the load resistor. So the voltage across that last resistor is your output. Okay, so the way it works is when the MOSFET is turned on, the input voltage charges the inductor. So the inductor builds up energy, it stores energy in its magnetic field. When the switch is turned off, the energy in the input and the energy in the stored energy in the inductor will charge the output. That's how it becomes boost, because now you are storing energy in your inductor, then you're using your input and your inductor to push up the output. So it's like, storing water and then also using like rainwater. That's one possibility. So that way you boost up your water table. That's one way to look at it. So with this little bit of like description, since this is what is usually called as a separate state circuit, because when the switch is on and the diode is on, you can have different states of operation of this. So there can be 2 states of operation or there can be 3 states of operation, right? Now in this case, he's put what is called as continuous conduction mode, but there is a possibility of having a discontinuous conduction mode as well. So the discontinuous conduction mode is when both the switch and the diode are turned off. That is one case where that happens. So in this case, like for example, the first equation is when the switch is turned on, right? The very first matrix equation.
No, sir, it is actually what we say average model. I directly jumped onto this average model, so not to utilize more time. So this is the steady state average model.
I see.
Both the cases has been used incorporated here.
I see. Okay.
Yeah. So this is for steady state. Basically, it is dIL by dt and dVc by dt. So since in steady state change is not there, so there is no change in inductor current or change in capacitor voltage. So if we have equated it to 0 for steady state, and for this is IL cap and VC cap is the error that we have during our steady state or control.
I see.
So I have not waveforms here, so it would have been very easy for us to understand. But basically, that IL dot cap and VC dot cap is the error that the typical waveform of inductor current, right? It is like charging up and charging down, a zigzag kind of wave. So if we so this is the average it is a steady state current. So it is like maybe I can.
The only thing I'm seeing here is that to simulate this, I guess you can still simulate it anyway. Continue with what it is. So you have not written this. You have not actually solved this.
I have not written each and everything, just for the sake of to keep it contact, and whatever we will require for modeling, that only equations I have kept.
Okay.
So that's why.
Okay.
I think at least for you it is clear what is what equation. Maybe not for Krishnan, but at least for you, I think it is clear.
Now from this, that normal x dot is equal to ax plus bu and y is equal to cx is like a very normal control equation. That is for any control portion. So what we have to now do is like this. We are saying that it is x dot is equal to a, or rather, it is x dot, rather ex dot, I guess. Or have you put it? No, you already put it as x dot, right?
Yeah.
Okay, so the first 0 should not exist.
My notebook where I have this is the notebook. Okay, I have imported basic packages, and this is the parameters. Like I have initialized it to 15 volts. Reference is, for example, 20 volts. LCR are 2 millihenries. D is 10 microfarads. R is equal to 100 ohms. Okay, and D is basic. It is basic formula of VO by VD. Okay, and IO is V out by R. In this case, I have considered V reference because that is what we want. Okay, so this is the computed values of duty ratio and output current. So this is a steady state model where this is A matrix, which is a 2 by 2 matrix. DS is also is a 2 by 3 matrix. Okay, and CS is 2 by 2 matrix.
Why are you using matrix and not array?
Actually, I tried using basic arrays, which is not part of NumPy as well. Basic, like
just Python
square bracket.
Okay.
Yeah, square bracket 0, minus 130 and so on. But it was not. Means I was getting lots of errors, and that I was not able to understand. So then I thought it is a matrix, so let's use matrix.
No, there is a np.array for array method. I have not used the matrix, but anyway, I guess it must be similar.
Yeah, even in NumPy library, they have means in documentation they have mentioned that it is preferable to use arrays than matrix, because in further updates they will be eradicating this method.
Yeah.
But since I am familiar with MATLAB and Octave, so I was familiar with this syntax.
Okay.
So for first run, I am using this matrix form, but maybe in wherever this discussion is going on, we will modify it.
Okay.
So C1 is the first row of CS matrix, and C2 is the second row of the CS matrix. This is the inverse of A.
Okay, now CS, just go up 1 minute. Let me see what is, if you can scroll up.
Yeah.
So you are using basically you're using x dot is equal to ax plus bu and y is equal to cx plus du, right?
Yeah.
Now, if it is using y is equal to cx plus du, the y is the output, right? Now
that is computed in further steps.
No. I'm just thinking about, see, for example, okay, can you show me your sketch? I'm just checking the output okay, so now if you look, the equations, above equations. So you're using x dot is equal to ax plus bu plus u, y is equal to cx. Okay, now in this case, what is your output? Your output should be the output voltage.
Yeah,
that is just VO.
Yeah.
Now, if your output is VO, y is equal to VO, y is the scalar.
Mm-hmm.
So therefore, if you look, you have chosen VO ID. What is this ID?
ID is equal to is input current.
I don't know. Do you need it? Do you need that? And how is that the output?
Yeah, it is required in the small signal model. See, here we require in the third column of V matrix, we require minus ID by C and VO by L. So these two values we are calculating here, and that we are using in the steady state model. So small signal model. So in small signal model is used to construct our controller or design our controller, but some values are taken from steady state model. So that's why we have to first design a steady state model, then compute output values and whatever values you require to design your small signal model, and then you put in this and you go forward designing your control. That's how we were taught in our college. So that's why I'm following this algorithm.
Okay, can you just go up once more, because I'm just checking the equations. So if you look a little more, go up to the circuit. Now, if you look, your ID and IL are the same.
Yeah.
So really speaking, you don't need another variable for that.
Yes.
Because you get what I'm saying, right? The current that is supplied by the source is the same as the current flowing through the inductor.
Yes.
So there is one problem in this model, is that the variables are not independent. Now, Krishnan, you can correct me if you want, but when you have a state space representation where the variables are not independent, then in that case, the rank of the matrix will not be full.
Yeah, I think I was getting some error which they were highlighting on rank of.
This is our old behavioral controller.
It may not. I don't know about the rank, but at the end, it will not be the minimal model.
Exactly.
So you will end up having states dependent on each other, and you are going to, if you are going to analyze properties of the system with this model, For instance, in a transfer function scenario, you will have pole zero cancellations.
Yes.
Sometimes.
So what you have is, it's like basically, just to say, is like this. You're aware of the state space method, right? So basically you have a space which has so many variables. Now you have chosen a certain number of variables. Now out of these variables, if your vectors forming these are not independent, then in that case you are having some of them dependent to each other, right? In the end, what happens is there is some variables which you cannot control. So basically they are dependent on others and there's nothing you can do to them. So that is potentially a problem that I see here. The only thing is that the variable ID is not an actual state variable, but is a variable that you are computing from something else. Now, from a control perspective, you may use it to regulate the current that is supplied by the source. For example, what usually happens is in power supplies, not only do you want to control the output, but you also want to make sure that you don't burn the input, because the input should not overheat and things like that. But even if you want to do that, all you need is your inductor current. You don't need the output current. You just need a limit on one state variable. So your output variable is the variable of importance that you want to regulate, and the inductor current is merely something that you want to place a limit on.
Okay.
You don't need to define another variable.
Yeah. So, but in small signal model, like it is the second equations. So if you can see the B matrix, in the third column of the B matrix, we have B0 by L and ID by L. So we require this third row of B matrix to go forward.
I don't see so, because from what I see, the two variables are the same. See, there is no need for the third variable. That's how I see it. See, Christian, you're on mute. You're talking.
Yeah, sorry. So what I see is, what he's trying to do is that he says that the ID has to be, acts like an input.
Mm-hmm.
But is there a relationship between ID and the voltage input that you know?
I don't think there is an actual relationship. There is a need to sort of control, because the ID multiplied by VD will be the input power. That is basically what it is.
Exactly. So what I'm trying to understand is, if that is not the case, then this part that is appearing on the B matrix would essentially be in the A matrix itself. Because in the A matrix you have IL, and you write those V0 by L and whatever ID by C, you have to add them into the A matrix, where it will get appropriately multiplied with IL. Multiplied or whatever, however you modify it. But at the end of it, it need not be a separate input, because you consider it as an input, but it is also considered as a state. So this is not how you can design the state space model. State space model will typically have a distinct nature of inputs and states, except in some weird cases.
Okay. So let's first see what I have done. Then we will discuss what modifications we have to do.
Yeah.
Okay.
Sure.
See this input number 4. We have C1 and C2. Because we require using C1 we are calculating this V out or VO. It is minus C1 into inverse of A inverse into V1, which is the first column of BS matrix.
Okay.
And for ID, CS2 into A inverse into B2. B2 means the second row of second column of B2 matrix, and IO. Okay, so by these calculations we are getting a VO and ID. Now this VO and ID is required in the third column of B matrix. If you can VO by L and ID by C. And why specifically this? Because our the main transfer function will be VO by D, because our output parameter is VO and our control parameter is D. Okay, so that D is associated with the third row of the B matrix. So this is required.
Okay, now the problem I see is that you've taken this matrix as absolutely true. I don't really see the case how it would be. That is the problem. I would say just try to investigate a little, because from what I see is that that column should not really exist. It doesn't do anything. State space is like this. What it means is that if D increases by an incremental amount, right, then what is the effect it will have on each incremental state, right? So you just have to split these up and re-express the equations. I don't think these equations are right. You can continue, but I don't think this will really, you may not get a result. I'm not sure how it is, but anyway, continue for now.
Okay, so for a small signal model, A is this, B is computed. Okay, now the problem starts here. What I am aware of how we should do is that once we get this ABCD matrix, okay, then we transform it, then we extract the transfer function according to our needs, like what is our output variable, it is VO, and what is our control variable, it can be VD also, but for now, for us, we are considering it should be duty cycle. Okay. For that case, we have to use this particular matrix, the rows of the matrix B, and third column of the D matrix and third column of the B matrix. Then only we will get VO by D. If we are considering the first row, then it will be VO by VD. So if we control the input voltage, it will give us the controlled output at VO. But we are changing in terms of duty ratio. That's why the third column of the B and D will change. We have to consider. So if we there is a steady, small.
It's called steady state space here to transfer function.
Yeah, state space to transfer function in signal package of Scipy. It returns numerator and denominator. Okay. So now there are two arrays. I am assuming this is the numerator and this is the denominator. So by observation, I am not able to understand what are these values. So from here onwards, I will require your help.
Okay. Okay. I will just have a quick look at SS2ATF in Python. But typically it will probably give the polynomial that is associated with this. But polynomial having I'll just quickly see what is that.
From what I see is, if you're taking the full matrix A, which is 2 by 2, right? Then you're taking B, but again 2 by 2. So B is 2 by 2. Now what is C? C is a full matrix, again 2 by 2, right? Yes. So you have a 2 by 2 matrix. You have two outputs, right? You have two outputs. You have two states, and in D, how big is your D matrix again?
D is actually 2 by 3, but here we are using only the third column.
Only the third, okay. So from what I see is, because your C, if you're having a 2 by 2 C, it's like Y is equal to Cx, what is the formula? C into Si minus A inverse into B, right? So if your C is 2 by 2, that is setting the number of rows of your resulting transfer function. If C is a single, like C, if you had just one row array, then in that case, you will have a single row. So it's like this: C Si minus A inverse into B. So if C is 1 into 2, is an array of 1 into 2, Si minus A inverse is 2 by 2, and B is 2 rows in one column, then the result will be one single polynomial. If you look at it, think about it this way. See, C Si minus A inverse B, if you just do the array mathematics, if Si minus A inverse is 2 by 2 array and B is a 2 into 1 array, then Si minus 1 into A inverse into B will be a 2 by 1 array. If C is a 1 by 2 array, then the result will be one polynomial, which is what you want. But because now C is 2 by 2, that is the reason why you're getting an array for the numerator as well. So this is the problem. The problem is when you're choosing C, you have to choose one output. Always when you do transfer function analysis, you have to
first row of this C matrix you have to use.
No, anyone. Choose which you want. Basically, you have two outputs. You are choosing one output with respect to one input. Always. So you have to map your input and output and choose what you want and take the input that you want. So you can find a transfer function between VO and D or between ID and D.
So here, okay, so this is our C matrix. Okay, so we want VO. Our output function is VO. Output variable is VO.
Exactly.
So do you want to say that we should consider only the first row of C matrix?
Yes.
Okay.
And at the same time, also for the D matrix, you should consider only one column. That is, which is the column that you are interested in. So if you are interested in D,
it is only one column.
Then it's okay.
And B, it is only one column.
Then it's okay. So then you can, So that's the thing. So for C, if you can choose one, then try see how it works.
Okay. So for C, first row. So in this case, just give me an error.
Okay, let us see. The input arrays have been coupled. Okay, let's go up and check again. A is D. Okay, see, using C, it's like C Si minus A inverse into A. What is the size of A? 2 by 2?
Size of it is 2 by 2. See here, it is 2 by 2 matrix.
A is 2 by 2, B is 2 by 2, okay. D is just trying to think what could be the problem. Anyway, tough to say now. We'll have to investigate later, but I would say that these are some issues which incompatible. We'll have to also look at what it is trying to do. If you look at Statespace.
Okay, so let's define what is the problem. Define what we want to achieve. So basically, our transfer function should be VO by D. Okay, so means VO cap by D cap. Okay, so here in this output matrix, VO is associated with first row. Okay, and in B matrix, D input is associated with third column. Okay, because D cap is the third variable. So third column is what we require for D VO by D. So what should be the A matrix and D matrix in that case?
So the D matrix is again the input should only be the single column which corresponds to the input that you want to consider. And the same goes for B. So always like you want to map your transfer function between an output and an input. So your output matrix should have the row corresponding to the output variable. Your B and D matrix should have the column corresponding to the input variable.
Yes. And for A?
For A, I think it should be the full one because it is considering the entire state. The only problem that I'm seeing, and this is from my past experience, if you look, we used to use Scilab, it would solve a polynomial matrix. Solving polynomial matrix is slightly complicated. Now here we are choosing a particular value of D and then calculating A inverse. So now do we know that A inverse exists?
Yeah, for small signal model.
For the small signal model in state space domain. See, you see state space continuous. There is a 0 in the diagonal. The first element, you see state space continuous in 30. Look at row in 30 and the out. So if you look at the out 30, you see element 1, 1 of the very first matrix, which is A, is 0. So your A matrix is singular, which means the inverse does not exist.
Okay.
So if you try to compute A inverse, you will have a problem.
Okay.
See, it is typically in transfer function, it is C Si minus A inverse into B. Right? So here, if you try to put S is equal to some value, then maybe it does. But again, I don't know what this thing does. That is a problem. If it is taking A inverse, automatically it will give an error because it's a singular matrix. If it is taking a polynomial matrix and trying to calculate it, but then again I doubt, because a polynomial matrix is actually very difficult to handle. Scilab also we used to struggle. Remember Srinivas?
Yeah?
Okay, we used to struggle with polynomial matrices.
Yeah. Polynomial matrices
are not easy to handle.
Especially for, this is what this multi out. So what do they do? So it's like Nemo systems. If you want to deal with in Nemo systems with, but you want to compute the trans functions, and you will end up getting that. But I was trying to do something with polynomial models. In fact, Swanand did something on that.
Yeah. Singular matrix, if one of the models. Yeah, so that's the thing. Yeah. So we can investigate, but something like this is actually a little complicated. It is very important that your matrices be single. At least you have to check for the singularity. Also, you have to check for the structure. For example, if one element is very small as compared to the other element, again, that can be a problem. So sometimes, let's say you have e raised to minus 7 and you have 1000. Now there is a problem because there is a huge ratio between your elements. So there is a lot of issues in these kind of control things. Okay. So to be able to get control, you have to define your matrices very well. First begin with.
Okay. So can we forget the actual part? So can we modify it in such a way that it can be solved further?
That is
I
the thing.
can understand how to do it in MATLAB or in Scipy or in Python. Then I will try for a particular application in my free time.
What do? You post on the Google group with the equations. We have to first express these equations in the correct form. So I would suggest that you post the actual calculation of the small signal model. Let us try to make sure that the small signal model is as efficient as possible.
Okay.
Then we can then try to express the state space transfer function.
Okay.
Yeah. Just one question in this. Have you added me in the Google groups? Because I sent a request.
I sent an invite, I think. Just check. It would have been just maybe a few days back.
Okay. Is it how it is? Okay. Yeah, because I will have a look at the equations.
Yeah, sure.
And see how it is. Because at the end, if you define clearly what you are trying to do, because I probably missed it, because I was actually looking at state space to transform. But at a top level, what are you trying to do? You're creating a state space model. Let's say you have a specific point, the state equilibrium point around which you are creating this model. That's why you call it a small signal model. Right? Now, what do you want to do with this model?
Okay, so basically, this is the plant is a boost converter. Okay, and I want to design a proportional integral controller. Okay, and I want to compute Kp and Ki values so that whatever is the step input, it will reach the steady state in this amount of time and it don't go in overshoot. Okay. So this is the main idea. A very basic problem that we solve in college, but since we are used to MATLAB and Simulink nowadays, so we don't go in much details and equations and all. Simulink does everything for us. So that's why I picked this for me, so that I will study this concept in detail, and also use Python to understand it. So basically, small signal model is basically it is the variation or the model which gives us the variation around steady state.
Yeah.
So during steady state, error is 0, but in steady state, it is giving us how much variation it is having during a steady state. Okay, there will be some ripple around the steady state. So that ripple is given by the steady state model, and using this steady state model, we define, we convert it to transfer function, then we cascade it with a PI transfer function, typical ki plus kps upon s, whatever it is, the transfer function of PI. We cascade it, we convert it to closed loop transfer function, and then by trial and error method or by root locus or Bode plot, we compute the gains of the Ki and Kp, and we put it into our model, and we observe the response of the system. So that's what I wanted to do.
Okay, perfect. So, so the first step, and if you don't do the first step, then you can't do the next steps. And so for that, we'll probably have to get the model right. So we will do some. I'm going to also take a look at things, because it's been a while I worked on transfer functions, because once you go into control theory work and you just use state space models, but it's actually, as you said, it's the thing that works in most of the industrial systems. So we will have a look at that, but just as he said, we will first write the equations correctly in terms of getting the model. Once we get the model, I think there won't be a lot of things we will just have to worry about doing Python.
Actually, for writing the equation, I have not referred any reference book yet. Okay, so these were my class notes, plus I was referring Professor Lumanan's video lectures on YouTube. You must be knowing him, maybe. He is a ISC Bangalore professor.
Oh, okay.
So
on
yeah,
power?
So power electronics.
Okay.
NPTEL lectures, I have referred to 3 lectures of him. So these equations are directly taken from his model, and in those videos he had actually simulated using these equations in I think so Octave and Octave. So in Octave it was working, but since it is only one-way communication, we can't communicate with the person, so we can't ask the doubts. Here we can do it. That's why I was I have not I have not simulated in Octave as well, because I was busy with other things as well. So directly I tried to model it in this Python and Scipy, using Scipy, but these errors were coming, so I thought we should discuss it. Actually, I was doing this since 2 weeks, I guess, before starting this series, I think.
Okay. Yeah, as he said, just send the equations on the group.
Yeah, I will send the equation. He's very late. Actually, he's my friend.
Okay, fine. Okay, cool. So anyway, since we have a few more minutes and we are almost done, the question is, what would you like to do next week? Next week we will have on Thursday, and then I will take a 2-week break. So next week, what do you want to do? It's open.
You say. Right now, I am totally involved in this problem because I want to solve this. So right now, on my free time, I am doing this. So whatever Krishnan want to do, we can do.
Yeah, I think something like this will take much more time, so it's better that we do offline. If you can start posting in the group, then it will also be good. So I already have your email. All we have to do is just add the equations there. We can start a thread.
I will write it properly on a page, and I will share the snapshot on the group. So maybe we can collaborate.
Okay, cool. So, coming to the topic.
Just a second.
Sure.
I'm just not sure if I got your invite. So was it in? It's a Google group invite or something?
Yeah, Google group invite.
This is the same group that we created during our band.
Same thing. Yeah.
Okay, I will send separately to you if you want.
Okay, sure. You can check.
See it, but we'll see. Okay, so one of the things, so we can do this in parallel, because this one, my guess is that you would not do anything more than using the existing commands. There will not be much Python related work that you'll have to do for your problem. So for your problem, once we set up the problem in place, ABCD, you put them properly, and then you set the closed loop transfer function, you set the KP, KB, KD values. You just have to run the simulations using the whatever simulation commands that you have. So you don't have to do a lot of Python programming in it. Definitely you need to know the commands. So maybe, as he said, maybe we can either take another Project Euler work, or we can check something on Kaggle.
Whichever. Whatever you like.
Yeah, because I was looking at Project Kaggle, Project Euler other works, and there are a lot of them, but most of them have a very similar approach. In the sense, you have to repeat some calculations until a certain number. And so, yeah, it's going to be nice, but you will not really do a different kind of problem. So we can even take like the Titanic problem in Kaggle to start with.
Yes.
So, or I don't know. It's been a while I went to Kaggle, and I have to.
Sure. So, okay. So what I can do is, should I share my screen?
Yeah. You know what the Kaggle is, right? So yeah, because I just don't want to be saying something.
So let's go to Kaggle. So let's go to the data sets. What would you like? The Titanic?
No, I mean Titanic is one of the first that they put. Maybe anything else, we can. Okay, let's see.
So let's look. Is there a trending new data set or something? So
I would like to do something which is not something that people are trying to fight it out, because
challenges are too much.
Have a result, because
exactly.
we'll take something which is which makes which is a little more standard.
Yeah. Usually it's better to have something which is...
So many COVID.
COVID. There's a lot of COVID.
Yeah.
Let's look at this hotel booking demand. So, okay, here is the data. So the data, if I look, I'm just trying to see if it's mainly just numbers, or is it a lot of... Okay, so it's a lot of numbers, which is good, because in the beginning, if there is a lot of characters, it becomes a problem. The reason is then you have to start going to natural language processing and things like that. So the good thing is there are numbers. So let's look at the content. So have you ever wondered when the best time to book a hotel room is, or the optimal length of stay in order to get the best daily rate? Actually, this is a pretty interesting problem, because even though we are not traveling now, we might travel sometime later. This hotel booking dataset can help you explore those questions. Okay, contains booking information for a city hotel and a resort hotel, and includes information such as when the booking was made, length of stay, the number of adults, children and or babies, and the number of available parking spaces, among other things. And personal data has been removed, that's fine. The data is originally from the article Hotel Booking Datasets, written by these people on February 2019, and it has been cleaned. Alright, so there are 32 columns. Let's have a look at the columns. So these are the columns. So one is it a hotel, that is a city hotel or a resort hotel? If the booking is cancelled or not. the lead time, that is the number of times elapsed between the entry date of the booking and the arrival date. So this is a very interesting thing. How much in advance should you book to get like a reasonable deal? Then the arrival date. So is it like peak season or is it like poor season? Whatever. Right? That's also pretty good. The year of arrival, the month of arrival. And then comes the date week number. Alright, so like it's Friday, Saturday, Sunday. Friday might be heavy. Tuesday, Wednesday might be peak. So that kind of thing. Yeah, so this actually looks like an interesting one. Again, this is just something I picked out randomly. You can always go back and check it.
This looks nice, yeah.
Yeah, this looks nice. Let me just quickly scroll and see if I can find something equally interesting. Corona hack. Air pollution in Seoul. Oh wow.
There was one thing we were looking at. I was trying. There was some earthquake prediction data set that was there.
I see.
But again, those things are problematic because you don't know whether what you're doing is right or wrong. Because those were mostly competitions from a lab where they have a data and they wanted people to do some analysis of the data.
Right.
So.
It's the movie trending YouTube.
This one does it have test data also? I mean, like, is it a competition or something like that?
I don't think so. This is not really that big. It's 16 MB, so it's decent.
Because we will not know if we have the answer correct or not.
Oh, okay. No, I think that is kind of okay because the main idea here is to sort of explore data. I don't think we can sort of try out if there is some machine learning. The problem with trying out machine learning is there is a lot of mathematics that we'll have to do, which may be a little too much. What is really nice, and this is what we did even in the webinar which I did on COVID, was that we actually just explored a video game dataset.
Okay.
So we just looked at, and we came up with some fairly interesting like inferences, you know. So like for example, the data provides average values for 6 pollutants, data measured. Okay, I guess we can pick any one unless you are picking on this. This is something we could start with. So let me just go back. Let me stop sharing. So that's one suggestion we have, that is hotel booking demand. If you have another, we can look into it.
Okay, yeah, let's see. The other one that I was looking at was mostly to do with earthquake prediction, but it was a competition. So
okay,
it was a competition a year back, or year or two back, was there, and then a couple of them when I was working before my PhD, I was working and we had done this disaggregation. So you get a single input and multiple sources are responsible for that output.
Okay.
And you try to disaggregate which of the outputs are responsible for it.
Oh, okay.
Which are the inputs are giving. So, but again, I think for us to gather around, I think the kind of data set you chose, like we want to try using Python. It's not like we are solving a great problem.
Yeah.
So we need to. So that in that case, what you suggest would be better. So you can if you want, you can just put a poll or something, and then or we will just choose one of the things.
Yeah, like there's nothing hard and fast. Whichever, even if you're willing to come up with something else, just make sure it has numbers significantly rather than text. Yeah. So like if you choose something with a lot of text, it's a bit of a problem because then you have to then decompose the text using natural language processing into vectors and numbers and things like that, which is a little messy. Because natural language processing is fairly different in terms of a different domain, fairly.
Yeah.
Because then you're talking about language. And,
I mean, text processing, I think we cannot do. We will stick to sensor data.
Exactly. Just numbers, either pollution data or whatever. Yes. Pollution data, numbers.
Can be converted to numbers.
Exactly. So that sounds pretty much like it. So yeah, I think we are out of time. I guess it's 7 p.m. So So yeah.
Just Nikhil, if you want, maybe you can send Shiva. You can connect me with Nikhil.
Oh, sure.
What is the name? I am searching on your LinkedIn actually.
Yeah, I will just show you. In my LinkedIn, I will show you. So do you see my profile now? You see Krishnan Srinivasan. Do you see my page?
No, actually we see something else. I think just see if you're...
Mozilla Firefox.
Ah, okay. Sorry. Sorry, I see. Okay. I don't know, but okay, let me just check.
And can you suggest me a book that will describe this steady state models and means what we are trying to do in better way? Because I am not having any book which other than this normal analysis pretty standard book we use.
But in what I mean, I don't know what. Okay.
Statespace.
The problem is that it is difficult to find anyone who uses this for power electronics. That is the major challenge. Like control, there are lots of books, but the problem with control books is they are heavily mathematical. They are written without absolutely any application towards electrical engineering. The people now who work in control is largely just hardcore mathematics. So the problem is to find something which is applicable to power electronics is the challenge.
What?
Is the challenge. It's very difficult to find a book which is like...
Oh goodness God, what do you want? Sorry. Okay, I will tell you, Krishnan S14. That is my number. Krishnan S14. So if you search in LinkedIn /in/Krishnan S14, you should get it. Okay.
S14. Yeah, I will type.
Yeah.
Because I tried, because there are many over 500 cars.
You can stop sharing now. There is a basketball player.
Whatever is there, I don't know.
Anyway. Yeah, okay, cool. Anyway.
Okay. Yeah.
So yeah, great. Another interesting session, though probably may not have been very productive because we could not solve the Python power electronics problem, but we solved the highly divisible number, so it was good. So
let's take as you said, let's take the hotel problem. Okay. And because I would prefer, like, if for instance we get to a point where when you leave before next week for a couple of weeks, because if possible we can do something before the next week significantly, so that we are prepared before that. We understand the data, we know manipulating a few things a bit here and there, and then maybe we can try discussing very specific things next week, so that before you come back, when you come back, we start a new problem.
Yeah.
It's not going to, like, 2 weeks, we can't keep it wait.
Yeah, that's fine. Yeah, that sounds good. All right, so guys, thanks everyone for coming. Is Darius still there if he wants to close it? No, he's not. So, okay, cool. Okay, so see you next week. And
I will continue to solve that problem. Sure. And if anything I will write to you both.
Okay, sure.
Let's see.
Okay.
Thank you.
Okay then. Bye. See you.